Okay, after we learn about the shear stress in moving fluids, now we will see what is the Newtonian fluid. So this Newtonian fluid is related to our developed Newton's of law of viscosity. So Newtonian fluid is a fluid in which the viscous stress arises from its flow at every point are linearly proportional to the local strain rates, which is the rate change of its deformations over time. So you can see here the graph between the rates of shear and the shear stress. So here we will have the slope, which represents our Newtonian liquids. So Newtonian fluid's viscosity will remain constant no matter the amount of shear applied for constant temperature. These fluids have a linear relationship between the viscosity and shear stress. The fluids that obeys the Newton's law of viscosity has a constant value, which are known as Newtonian fluid. So these are examples of the Newtonian liquids. So we have water, mineral oil, and gasoline. However, how about the non-Newtonian fluids? So the non-Newtonian fluids is actually the fluid that does not follow Newton's law of viscosity. So that means its constant viscosity is independent of the stress. If you can see here, it doesn't have the straight line curve, but it changes according to their characteristics. So although the concept of viscosity is commonly used in fluid mechanics to characterize the shear properties of fluid, it can be inadequate to describe non-Newtonian fluids. So there are best studies through several rheological properties that relate stress and strain tensors under many different flow conditions, such as auxiliary shear or attentional flow, which are measured using different devices or rheometers. So when shear is applied to non-Newtonian fluid, the viscosity of the fluid will change. For the non-Newtonian fluid, we can divide it into two, either time dependent or time independent. So examples of the time dependent fluids are shear tightening, or we call it as pseudoplastic, shear thickenings, dilatants, or lastly Bingham. So for time independent, we have thiozotropic aerotactics. Pseudoplastic, or we call as shear tightenings, is a non-Newtonian behavior where the viscosity decreases under shear strains. It is sometimes considered synonymous for pseudoplastic behavior and usually defined as excluding time-dependent effects, such as thiozotropy. So let's see the video here. So the examples of the pseudoplastic is the condensed mix. So if we shake for many times, in the case of condensed mix, so it will increase their shear force among the particles. At the end, the viscosity will be reduced, so we increase the ability of fluid flow. So dynamic viscosity decrease as the rate of shear increase. So as we introduce some force, it will become more easier, less viscous for this condensed mix. Other examples, we can see we have paint, whipped cream, mix, and ketchup. Okay, you can see the video here about the condensed mix. So as we introduce the mix, here it is more viscous as we increase. After The next examples of non-Newtonian fluid is dilatant, which also called shear thickenings. So as we increase the viscosity, the rate of shear strain will also increase. And so in this example, we use cornstarch and water. So let us see. So when we introduce our cornstarch, it turns into more viscous, like solid structure at the ends of the mixings. Other examples, here we have silica and polyethylene. So let us see the video of mixings of cornstarch and water. You can see it is become more viscous. Okay, next is Bingham. Bingham is a physicoelastic material that behaves as a rigid body at low stress, but flow as viscous fluid at high stress. So it is named after Eugene C. Bingham, who proposed its mathematical form. So in this example, the toothpaste has been pressed to flow out the paste of its container. So certain forces are introduced, or we call it as critical stress, before the flow can commence. So without the enough force, you will not see the paste flow out. Other example is memory foams and also mayonnaise. Next is thesaurotropic. So thesaurotropic is a time-dependent shear thinning property. Certain gels or fluid that are thick or viscous under static conditions will flow, which become thin, less viscous over time when shaken, agitated, stirred, or otherwise stressed. Okay, you can see from this video the thesaurotropic. So others example of thesaurotropic here: drilling muds, honey, and ink. So it's originally is thick. So when we shake, it becomes less viscous. Okay, lastly, the rheopatics. Rheopatic or rheopatics is the rare property of some non-Newtonian fluid to show a time-dependent increase in viscosity. So the longer the fluids undergo shearing force, the viscosity become higher. So there are other examples as lubricants and body armors. And okay.